Hello, I'm Steve Reyes, Product Manager for Anritsu Company. Today I wanted to demonstrate how we perform on-wafer 4-port differential VNA measurements up to 145 gigahertz using the VectorStar VNA. So we're going to first talk about the system configuration and the different options that we have to configure a 4-port differential broadband system. Then we'll get into the actual setup, frequency parameters, etc., as well as go through the calibration process and the different options that we have for providing a calibrated system. And then we'll go and talk a little bit more about the different types of measurement capabilities we have using VectorStar in a differential setup. So the system comprises of the VectorStar VNA, which starts off as a baseband system operating from 70 kilohertz to 70 gigahertz. We also go to 20 gigahertz, 40 gigahertz, as well as 70 gigahertz. And so making measurements either in 2-port or 4-port is possible with VectorStar in a setup up to 70 gigahertz. Then, if we wanted to go into the millimeter wave range and do a broadband measurement, we can sweep from 70 kilohertz all the way up to the millimeter ranges that we covered, which is 110 gigahertz with operation to 125 gigahertz, or up to 145 gigahertz with operation up to 150 gigahertz. So adding the millimeter wave modules is what's key to the system configuration doing a broadband sweep. And we do that by adding the millimeter wave modules, which are nonlinear transmission line modules developed by Anritsu, which provide excellent raw directivity, power, dynamic range, and noise floor. To drive the modules, we add a millimeter wave test set. So we can go from a 2-port baseband system at 70 gigahertz, add later the millimeter wave modules with the test set to then sweep up to 110 or 145 gigahertz. Then, if we wanted to increase our port count from 2 to 4, we can then add 2 more modules to have 4-port broadband measurement capability. So, of course, if we have 2 more modules, we'll need another test set to do that. Also, in order to increase our baseband port from 2 to 4, we add a 4-port test set. So, in total, we have 4 instruments that are driving the modules in order to do our 4-port differential, 70 kilohertz to 145 gigahertz in this case. So as I was mentioning, the modules are developed by Anritsu. They're nonlinear transition line modules, and they are very compact in size so that it makes installation on a probe station very easy and convenient. You can see that we have 4 modules connected on our Anritsu brackets that are connected then to the differential probes. So in this case, the probes are the GGB probes operating to 145 with a 0.8 millimeter connector. So getting back to the 110 versus 145. So 110 is covered with a 1 millimeter connector. And the 1 millimeter connector can go up to maybe 130, let's say, gigahertz, but with modem. And so if you wanted to go to higher frequencies, up to 145, you need a smaller geometry connector, which is why Anritsu developed the 0.8 millimeter connector. And so with the 0.8 millimeter connector, we can go up to basically above 150, up to 160 gigahertz or so. So the modules then are performing up to 150 with the 0.8 connector. Now, in order to make connections to the differential probe, we need cables, because you can't have 2 modules connected directly to the probe at the same time. For 2 ports, we can connect our modules directly to the probe for a cableless high dynamic range measurement. But in the case of a differential, we'll need to use cables, which is why we developed the 0.8 millimeter cables with the connectors. So that's what we have here is the pair of modules connected by cables to the differential probe in order to get our differential on-wafer measurement with calibration. So again, going back to the modules, so we have 2 different versions. We have a 110 gigahertz version with 1 millimeter, going up to 125 gigahertz, and then the 145 with the 0.8 going up to 150 gigahertz. And you simply are choosing the module for the frequency coverage that you need. It's the same system. Basically, I can switch this between a 110 and 145 just by switching the modules. So it's a very convenient way to upgrade your system from 70 to 110 to 145, from 2 ports to 4 ports. So it's a very flexible, economical system because you don't have to buy a 4-port option inside the baseband in order to upgrade later to a 4-port system broadband. Okay, so getting back to the setup, so we have our modules connected to the probe. They're differential probes, and we're going to do some calibration using a GGB calibration substrate. And so we'll be doing a calibration and setup, which will show you basically how we go through the process of calibrating the system for differential measurements. So for setting up the system, we first want to go through the different parameters in order to configure it for the type of measurement we're going to be making. The good start point is going to be in frequency. So we'll set up our start-stop frequency. In this case, I've got 70 kilohertz to 145 gigahertz with 500 points. And if we wanted to concentrate our points in certain areas for the DUT measurement, we could switch from this linear display frequency sweep to a segmented sweep. And in segmented sweep, we'll then be able to program specific frequency points, increase the number of points in certain areas, etc. So in this case, we'll just settle with the linear frequency sweep. Next, we would set up the power, and in this case, I have minus 15 dBm. We can do anywhere from about minus 10 to minus 50, minus 55 dBm. So in the millimeter wave modules, we have an electronic AOC control. So we are actively engaging in AOC power leveling as we're sweeping. We don't need lookup tables, etc. And with the wide range of control that we have, we can get it all the way down to minus 50 dBm or even lower in order to measure very sensitive devices at very low power levels. Okay, so the power we have now set. Other areas of interest would be, for instance, averaging. We set our IF bandwidth. In this case, I just have it for 1 kilohertz, but you could set it to 100 hertz or whatever dynamic range requirements are needed. So once we have our frequency and power and averaging set up, then we're ready to start setting it up for the display that we want to look at. So this is where the response characteristics are configured. And it depends on the types of measurements that we're going to be making. In this case, we're going to be doing differential measurements. So we have a mode called mixed mode, which gives us the ability to set up our 4 ports for the types of devices that we're going to be measuring. They could be single-ended measurements or differential. They could be mixed mode, so we can do common mode measurements as well. So here's where we would configure our 4 ports for the types of DUTs that we're going to be measuring. In this case, I've set it up for 2 differential pairs and set up for the standard SD1D1, SD1D2, SD2D1, and SD2D2. And so we have 4 traces configured. So we'll go ahead and close that. And the traces are entered here, and we can go up to 16 traces. We also have 16 channels. So the different channels can be complete new VNA setups with different calibrations, different application measurements, etc. In this case, we're only doing 1 channel and 4 traces for the 4 differential parameters. And that's basically all we need to do to set up the system, getting ready for the measurement. So next, we're going to be doing a calibration, and first we do the setup for the calibration. So we go to our calibration menu, and here there's a number of other options and choices we have to configure the system for different types of calibrations, different types of de-embedding tools, etc. Like for instance, we have de-embedding tools for our 4-port devices. If you're using 4-port networks and you want to de-embed your test fixtures, you can go into the de-embedding routine and make measurements or do a calibration with those test fixtures and extract those out while you're doing your DUT measurements. So these are some of the things that are also available as part of the VectorStar system capability. So to do a calibration, then we go into our calibration mode, a manual calibration, 4-port. And here's the standards setup. But before we do that, we want to confirm that it's set up properly for the calibration that we want to do. So we go to Modify, and here's where we choose the type of calibrations. And so for on-wafer measurements, broadband measurements, we pretty much always go with LRM. It's a very quick and easy way to get very accurate on-wafer calibrations. Other choices that we make available are SOLT, but in that case you need a very good termination in order to establish very good effective directivity in your calibration. Since there aren't that range of good loads all the way up to 145 gigahertz, that's not going to be the best choice. There's also offset shorts. If it's a coax measurement, we might choose to do the combined SOLT with triple offset shorts, and that is actually supported in the calibration kits that we offer for the 0.8 millimeter connectors. So again, in this case, we're going to be doing LRM. So LRM is basically it's an alternative to the TRL, but in TRL, in broadband on-wafer measurements, you're not really able to get a good true through connection. And so the LRL is just simply a line measurement as well as your reflection and your match or load. So LRM is what we're selecting here, and then this is where we would go in and configure for LRM. And so what we would do is set up for the port configuration. What we have done in this setup is configure it for ports 1 and 3 and 4 and 2. So with VectorStar, in a differential setup, ports 1 and 3 can be either driven with a single source or with a dual source. Single source will give you full S parameter corrections of a 4-port device, differential devices, when they're operating in the linear region. If you're looking at nonlinear devices, differential devices, you may want to go into what we call true mode operation. And there you have control of the phase offsets between the 2 ports. So between ports 1 and 3, we have the ability to drive the 2 sources with a fixed batch-corrected phase offset so that we can do true mode stimulation of the DUT, especially when it's in a nonlinear mode operating condition. And so that's why we have it in this particular case set for ports 1 and 3, so that if we choose later to do a TMS operation, we're set up for that. So that's where all of this takes place in terms of configuring our port, is based on the physical location of the 4 modules will determine where our throughs are during the calibration. So we first establish our port connections for the throughs. Then we set up our calibrations of the 4 ports. And so there's a Cal A, Cal B, but basically what it is setting up our calibration in terms of things like, for instance, the reference plane location. We can set it up for end of line, or middle of line. At end of line, we are going to be calibrated at the probe tip itself. In the middle of line, if your line is the same length as the path to the DUT, then you can calibrate using middle of line and have the test port calibrated to the DUT itself. So that's why the choice between end of line and middle of line. Then the other things that we will set up are the line description. So in this case, the cal substrate, the CS2 GGB cal substrate, has a delay of 4 picoseconds. And so we set up for the delay of the line and enter 4 picoseconds for that line length. Then for the match, we define that we're using a match, and we can improve on the model of the match by entering the coefficients of that match or that load into our algorithm. And so this is where we would input the coefficients of the load and use that during our calibration. And then finally, we define the reflection type, whether it's an open or a short, or it could be both. So in the case of both, that's what we would call ALRM, Advanced LRM Method. And that just gives you more correction algorithms that will give you a little bit improvements in your calibration method. For this case and for this demo, we'll just select the short only. Okay, so that's basically it for setting up for the calibration. And we exit that and then go back to our calibration menu structure so that we can set up for the different cal standards and do that measurement next. So before getting into the actual calibration, we want to first set up our probes and make sure that they're aligned properly. One thing to do initially is to confirm that you have good position on the tips relative to the actual cal standards. And usually you'll find a mask that will allow you to do that and will help facilitate the actual alignment of the probes. You want to make sure that they're parallel and that the DUT or the calibration substrate is in line with your probes. The other thing you would want to do is confirm that the planarity of the probes are proper. So in other words, you don't have one edge or one side touching down before the other and creating an imbalance in the ground contacts, especially when you get into the differential probing environment, because as you can see, your ground signal, is quite a wide stretch. And if I'm touching down on this ground and barely touching here, I end up with a poor ground for my signals. And that could be one of the issues in your final calibration results or even measurement results. So you want to set the probes up properly, and you may want to touch down on other pads that are not as important to verify that the touchdowns are correct and everything is in proper alignment. So now that I've got things aligned with these probes and this cal substrate, I can then move on to my devices itself. And so again, you can see here that I've got a number of devices to go through, and I'll first select the reflected device and then start making my measurements. So now we're ready to start making measurements of our calibration standards. So I'll first go to the reflection devices and set up for my short. And so now we can go and call up our shorts and land on them in order to make our calibration of our reflection devices. And here we're just simply touching down on this short and starting our measurements of the short by clicking on the different selections. and then go to our next set. And that's it for the reflection devices. Next, what I'll do is the through reciprocal. Now, if you recall, in the setup of the throughs, we selected ports 1 and 2. So remember that this is port 1, this is port 3, that's port 4, and that's port 2. So we now have a through where we need to connect between ports 1 and 2. This is our standard through standard, our normal through standard. And you can see we're not doing a 1 to 2 through connection. So what we need to do in this cal substrate, they have single line throughs, and that connects to my port 1. And now I simply have to offset my differential port 2 so that it matches the proper single-ended ports. And so there I have my module port 1 and module port 2 connected through this through, and that's what this through reciprocal is going to require. So I can touch down on this measurement. Select it. And then that completes that measurement. So now that we've completed the through reciprocal measurement, we want to move on to the matches. Okay, and so now I've repositioned my probes to the match standards, and since I haven't readjusted the differential port 2 yet, it's offset from where we want to be. So now I'll need to go back and set up my differential probe 2 so that it's landing properly on the match standards. Touch down on that and go in and perform our match measurements. And these are for ports 1 and 4. And now we go to ports 2 and 3. And since we've touched down on the two standards simultaneously, we can just go right through to the two different differential ports to make the measurements at the same time. Okay, so now all that's left is to measure our line, our through line. And so now I'll position over to the through standard right here. Okay. And here it's important to make sure that the separation is close to where the standard is defined. So in other words, with the proper skating, when you land on the throughs, you should be exactly 4 picoseconds apart. If you come in too far, for instance, and then land and skate inwards and you end up with less than 4 picoseconds of separation, that's going to throw off your calibration. So this part is fairly critical, and again, it goes back to the initial calibrations when you were using that alignment tool in order to correctly identify the skating amount so that you get the right amount of separation between the two ports. So now we're positioned properly on our line, and we touch down on our line, and now we can do our port 2, 3 through connection. And when you do your through connections, they typically will take more time because there's a lot more processing. You're basically looking at a number of different characteristics of the standard in order to extract out all the error terms in your system. And so now we've finished with the port 2.3, and we've gone over to the ports 1.4, and we make a measurement of ports 1 and 4 of the standard. And then once it's finished with that, then we're done. So there is the option of doing an isolation, but we found at normal operating levels and typical types of structures, isolation isn't usually needed. So it's optional in case you do have certain situations where your DUT substrate might have some isolation issues in it, and if you're able to duplicate that, then you may be able to use that capability in your calibration structure. Okay, so now we just simply click on Done, and that will give us the ability then to evaluate our calibration, take a look at the characteristics of the through line. Now, of course, this is the Cal standard, and what we would want to do is go to a different through in order to do the true evaluation of the calibration. The next thing we would also do is, if we want to start looking at stability of the system, we might go to a different through, store that into memory, do a data divided by memory, and look at it over a period of time, and that would give you a good stability. Another thing you could be doing at this point is doing the number of touchdowns in order to see what the repeatability of your probes and contact on pads are. So that's concluding basically the calibration and setting it up, getting ready for our DUT measurements. So now we have the DUT mounted on the chuck, and we're performing our differential calibrated measurements. So you can see right off the advantage of having such a small, compact millimeter wave modules. It gives us the ability to install other devices such as DC probes. So being able to, on the same platen, be able to mount the DC probe positioners and get up into the DUT in order to touch down on your DC pads is quite important. If I had larger millimeter wave modules in a differential configuration, it would more likely take up the entire platen, and I wouldn't have the option of installing the positioners for DC probing. So the size and compactness, as well as the performance, is quite valuable for differential probing on wafer stations. The other thing that we are providing with VectorStar these days are the ability to do things like differential noise figure measurements. We are now able to do differential noise figure up to 70 gigahertz in the baseband system and up to the millimeter wave frequencies using the millimeter wave receivers. In the nonlinear transmission line modules, we're able to bypass the couplers, which are typically found in millimeter wave modules, in order to improve on the noise figure of the receiver. And so with that special receiver capability option, we're able to do differential noise figures up to 110 and even 145 gigahertz. So that is something that's being considered and thought of as being quite valuable in the ability to characterize differential LNAs, for example. So that basically is the entire measurement process from setup to calibration to measurement of our system. And again, we can go up to 110, 145 gigahertz in either 2-port or 4-port. And we can be flexible enough to upgrade your 70 gigahertz 2-port to a 145 gigahertz 4-port system. Okay, and thank you very much for your attention. And for more information, please contact us at www.anritsu.com. Thank you.